Welcome to the deep dive. We cut through the noise, get straight to the sources you care about. Today, we're looking at something really mind-bending in AI, planning.
Yeah, usually when we think AI planning, we think, text instructions, step-by-step guides.
Exactly, like a recipe or directions. But what if AI could plan visually, like just using pictures, no words at all?
It sounds intuitive, maybe, like how we might mentally picture rearranging a room. But the sources we're digging into show that most current AI, even the big multimodal models that see images, they actually do their main reasoning in text.
Right. So they look at the visual world, but then they have to translate it into words inside our head before they can think about it or plan. The paper calls this the modality gap.
It's a really key concept they emphasize, this reliance on grounding everything in text first. They argue it hinders the model's ability to capture visual features and state transitions. Basically, even if they see, they don't naturally think in pictures.
Uh-huh. And you can immediately see where that might cause problems. Think about navigating a really complex maze or understanding how gears mesh together.
Yeah, describing that stuff accurately in words can be super awkward. The sources point out verbal descriptions may struggle to accurately capture complex spatial reasoning relationships.
It's like, yeah, trying to teach someone intricate choreography just by talking about it, it loses something.
Definitely. And there's a nod here to cognitive science too, right? Like dual coding theory, the idea that humans have both verbal and nonverbal, like visual ways of thinking that can work independently. This research kind of explores if AI can tap into that visual channel more directly for planning.
So the big idea, the core academic contribution here is this new paradigm they call visual planning. And it's simple on the surface, but powerful. The plan isn't text, it's a sequence of images.
Exactly. It's executed via sequences of images that encode step-by-step inference directly in images. Language just isn't part of the planning output.
So instead of reading a list, you'd see a series of pictures showing the solution unfolding. Like, given image 1, the AI generates image 2, then image 3, visually showing the steps.
That sequence of images is the plan. Starting with an initial image, $0, it generates this visual trajectory through hat.
Okay, so for this deep dive, our mission is clear. We need to unpack this for you, understand how they actually built an AI to do this. We really want to focus on their innovative reinforcement learning method.
Right, the VPRL framework.
Yeah, and then look at the evidence. Does it actually work better than text for visual tasks? And what are the bigger implications and, the current limits?
Sounds good. And let's just double click on that modality gap again, because it's fundamental. Even the really advanced MLLMs, they take in images, video, whatever. But the reasoning,
Still text.
still text. Purely in the text format during inference, as the source puts it, captions, rationales, plans, it all comes out as words.
So the image goes in, gets processed, but then hits this translation layer before the AI can really think strategically about it. And that translation can lose fidelity.
Precisely. You lose nuance, subtle spatial relationships, the exact way things change visually from one step to the next. This is especially bad for tasks that are inherently visual, spatial, physical.
Okay, so problem identified. Text reasoning isn't always best for visual problems. Solution proposed. Visual planning, thinking in pictures. How did they test this? They needed a specific kind of AI model, right?
Yeah, this is a clever experimental design choice. To really isolate visual reasoning, they used LVM3B, a large vision model.
And the key thing about LVM3B.
It was trained only on images and video frames. Zero text data went into its training.
So no hidden language skills influencing the results. They wanted pure visual thinking.
Exactly. It let them study visual planning without language being a confounding factor.
Makes sense. But okay, the big question, how do you train a model like that to generate not just an image, but a sequence of images that represents a valid, useful plan? How does it learn what comes next visually?
That's where the core academic innovation lies, their framework. Visual planning via reinforcement learning, or VPRL.
Okay.
It's a novel, two-stage RL approach, using something called Group Relative Policy Optimization, or GRPO, to fine-tune the vision model for sequential image generation, specifically for planning tasks.
RL makes sense for planning, learning strategies, exploring options. So break down these two stages for us.
Okay, stage 1 is called Policy Initialization. And it's unusual. Think of it as an exploration warm-up. They don't train it on perfect, optimal plans yet.
No. What then?
They train it on sequences from random walks in the environment.
Random walks, like just wander around visually. Why random? Seems backwards for planning.
This is a key insight. The goal here isn't to learn the best plan, but to teach the model how to generate valid sequences of visual states. What does a step look like? What happens visually when you interact with something?
Ah, okay. So it learns the visual rules of the world first.
Exactly. By seeing lots of random but valid transitions, it develops the ability to generate plausible next visual steps. And this is crucial. It retains exploration capability. It doesn't just memorize one good path.
So it learns the visual language, the grammar of the environment, without locking onto a single solution too early. The paper calls this an exploration-friendly initialization.
Precisely. It's primed to explore in the next stage. Which brings us to stage 2, reinforcement learning for visual planning.
Okay, now we leverage that exploration.
Right. The model, using its ability to generate plausible visual steps, now proposes a group of candidate next images. Think of it like sketching out a few possible next moves.
And then the RL ticks in with feedback.
Yes. The RL system evaluates those proposed visual steps. Are they good moves towards the goal?
But yeah, how do you evaluate an image? It's not like a simple text action. Images are complex, high-dimensional. How do you give useful feedback?
This is probably the most innovative part, academically speaking, their progress reward function. Is how they bridge the gap between complex visual output and a clear learning signal for planning.
Okay, walk us through that, the progress reward.
They do basically 2 key things. First, for each generated potential next image, they have a function, let's call it the parser mathcal, that looks at the visual change from the current image to the proposed next one.
Okay.
And it figures out, based on that visual change, what discrete action just happened. In their experiments, this was rule-based, like, did the agent icon shift 10 pixels up, means move up, or did the key icon disappear from this spot, means pick up key.
So it translates the pixel changes back into an understandable action, step 1.
Step 1. Step 2, they use something called a progress map. Let's call it MASCAL. This map essentially scores every possible visual state in the environment based on how close it is to the final goal state. Think shortest path distance, often found using breadth-first search.
Got it. So for any image, the map tells you roughly how many steps away you are from the solution.
Exactly. So now you have both pieces. The action the visual change represents from MASCAL, and you know if the resulting visual state is closer to the goal from MASCAL.
Okay, putting it together.
Right. They categorize the visual transition based on these 2 things. Is it an optimal action, meaning it's a valid move and it reduces the distance to the goal according to the progress map?
Moving closer. Good.
Or is it non-optimal, meaning it's a valid move, but it doesn't reduce the distance? Maybe it's a necessary detour or just staying put. Still allowed, but not directly progress.
Okay.
And the third category, invalid. This is when the generated image violates the rules. The agent walks through a wall, disappears, picks up an object that isn't there. Bad moves.
And the rewards line up with these.
Perfectly. Optimal steps get a positive reward for +1. Non-optimal, valid steps get 0 reward, no penalty for exploring or taking necessary detours. But invalid steps, they get a big negative penalty, like -5.
Ah, so it strongly discourages impossible or rule-breaking visual outputs.
Exactly. This reward structure directly trains the model to generate sequences of images that are not only visually coherent and valid within the environment's rules, but also actively make progress towards the desired goal state. It's a very clever way to apply RL directly to the visual output for planning.
Okay, that is clever. Connecting the high-level goal to the low-level pixel generation via this structured reward. So the big question, did it work? How did VPRL actually perform in experiments?
They tested it on a set of grid world tasks, FrozenLake, Maze, and MiniBehavior. These are standard-ish benchmarks, but perfect here because planning and the results of actions are entirely visual. You see the agent move, you see the ice break, you see the object get picked up.
Good testbeds for comparing visual versus text planning. And they measured success how?
2 main metrics, exact match or EM superstruct. Does the entire generated sequence of images perfectly match the shortest optimal path? One wrong image, and it fails.
Okay. And the other?
Progress rate, or PR. It measures the fraction of correct competitive steps from the beginning of the plan compared to the optimal path length. So it gives credit even if the plan goes wrong later.
Got it. So what did the results show? Finding number 1.
The biggest headline. Visual planning absolutely crushed textual planning on these visual tasks. The paper's blunt. Visual planners, VPFT and VPRL, achieve the highest scores on all tasks, outperforming all language reasoning baselines.
Even the supervised visual planner VPFT, basically stage 1, trained on optimal paths instead of random walks, even that beat the supervised text planner by, over 22% average EM?
Yeah, and then VPRL, the full 2-stage RL approach, just blew it out of the water. It achieved over a 40% average gain in exact match compared to the text-based baseline across the tasks.
Wow. And how did the really powerful powerful language models like the LLMs people use every day do.
That's maybe the most telling part. Even something like Gemini 2.5 Pro, which is known for strong reasoning, really struggled. The sources say it scored almost below 50% on both EM and PR for the harder maze and MiniBehavior tasks.
So for tasks where the logic is inherently visual and spatial, forcing that logic through the text modality really seems to be a major handicap.
That's the clear empirical takeaway. It validates the whole premise of visual planning for these kinds of visual-centric problems. It avoids that modality gap penalty.
Okay, that's finding one. Visual beats textual. What's the second key result?
The power of reinforcement learning, VPRL, the RL method, was significantly better than just the supervised visual training, VPFT.
How much better?
A substantial improvement of more than 20% across all tasks over the supervised baseline VPFT. VPRL got near-perfect scores on the simpler FrozenLake tab, like 91.6% EM, and really strong results on the complex ones too, around 75% EM.
And the why behind that boost is the RL itself, right? The exploration and learning from consequences.
Exactly. The paper credits the RL stage, guided by that progress reward, for allowing the model to freely explore diverse actions and learn from their outcome. This helps it uncover the underlying rules and patterns of the environment much better than just mimicking demonstrated optimal paths, which is what supervised learning does. It's a key advantage of their RL approach.
Okay, finding 3. This one was about robustness, how well they handled complexity.
Yeah, this was interesting. They increased the size of the FrozenLake grid. What happened to the language models?
They fell off a cliff performance-wise. Gemini 2.5 Pro went from like 98% EM on a tiny 3x3 grid down to below 40% on a 6x6 grid.
A really sharp drop. It struggled to generalize its text-based plan to a larger, unseen space.
But VPRL.
Much more stable. Its performance curve was much flatter. It still nailed 82.4% EM, even on the 6x6 grid. This shows way better robustness and generalization. The visual planning strategy it learned seemed to scale better.
That suggests it's learning something more fundamental about navigation, not just memorizing paths for one size.
Seems that way. Although, interestingly, on MiniBehavior, visual planners actually got better as the grid got bigger, maybe due to some repeating structural patterns in that specific task.
Huh. Okay, and the final key finding, this ties back directly to that reward function. VPRL got better at not doing impossible things.
Significantly better. They looked at the invalid failure ratio, how often a plan failed because it included an impossible visual step, like walking through a wall.
And the supervised visual model, VPFT, made a lot of those errors.
Yeah, pretty high rate, 60–80%, because it only saw good paths. It never explicitly learned don't walk through walls.
But VPRL, with that negative reward for invalid stuff,
Learned to avoid them. It cut that invalid failure rate by at least 24% in all cases. So the RL reward scheme demonstrably worked in teaching the model to respect the environment's visual rules.
and supporting all this, the ablation study confirmed that stage 1, the random walk initialization, was actually necessary, right? You couldn't just jump straight to RL on optimal paths.
Correct. They showed that skipping stage 1 led to much lower final performance. Analyzing the model's internal state, they found that stage 1 maintained high exploration entropy, like the random policy, while just training on optimal paths, VPFT quickly killed off exploration. That initial exploration phase was crucial for the success of the stage 2 RL.
So that two-stage design wasn't just arbitrary, it was key to making the whole thing work. Okay, let's look closer at the errors. What kind of mistakes did the visual planners make, even VPRL? And how did they compare to language model failures?
Well, visual planners could still take suboptimal detours sometimes. And they weren't perfect at avoiding all invalid moves, though VPRL was much better. But the types of errors highlighted in the case studies were revealing.
How so?
Language models seem prone to errors stemming from, like, misunderstanding the environment's layout or size, or just losing track of the current state because their reasoning is detached from the direct visual feed. This could lead to suggesting impersonal moves or getting completely lost.
Because their internal map is made of words, not the image itself.
Pretty much. Visual planning, because it's reasoning directly in the visual modality, while reflecting the visual states per action, tends to avoid those specific kinds of state tracking or grounding failures. The analysis also showed VPRL could be more flexible. It might take a detour, but then recover, whereas the purely supervised VTFT model might just get stuck if the optimal path was blocked. RL gave it more adaptability.
This really does feel like a different way for AI to operate. What do the authors see as the broader implications here? Where could this lead?
They're quite optimistic. They see this opening up new possibilities for the way human and AI system interacts, especially in fields where seeing and acting are tightly linked. Think robotics, navigation, and assistive technologies.
Yeah, anywhere an AI needs to understand and plan actions in a physical visual space, like a robot navigating a warehouse or a self-driving car planning its maneuvers.
Exactly. They frame this as a strong foundation for AI that can integrate both verbal and nonverbal thinking, but crucially, they argue we need to strengthen the visual component, which this work demonstrates is powerful but underdeveloped compared to language.
Of course, it's still early days. They acknowledge limitations, right?
Oh, absolutely. They're clear this is foundational. One limitation is the model scale. They used LVM3B because it was available in purely visual. They haven't yet integrated this into the massive, truly multimodal models that generate both text and images natively. But they believe the visual planning paradigm can be extended.
So the future might be AI that thinks in pictures and words, switching or combining them.
That seems to be the vision. Another practical limit is computation. Generating sequences of high-resolution images is just computationally expensive compared to spitting out text.
Yeah, inference time could be an issue.
Right, so future work needs more compact image representations, ways to capture the necessary visual planning information more efficiently.
Makes sense. Any other major limitations?
The third one they highlight is that state action parsing step, figuring out what action does this visual change represent. In this work, it was pretty basic, rule-based pixel watching.
Not robust enough for the real world.
Probably not. For complex scenes, you'd need much more sophisticated computer vision, object segmentation, contour tracking, etc., to reliably interpret visual changes as actions.
Okay. So lots of engineering needed to scale this up, but the core concept seems powerful.
That's the feeling. They call for building more holistic multimodal thinking systems, ones that really leverage both visual and verbal reasoning pathways, maybe even showing interleaved steps of both. But the key takeaway is the need to seriously invest in the visual reasoning side, which this paper gives a strong proof of concept for.
So wrapping this up, this research presents visual planning powered by this novel VPRL framework. It's got this clever two-stage training using random walks for exploration, then RL with a specific progress reward. And the results are compelling. It shows AI can effectively think and plan directly in images for visual tasks, outperforming text-based methods and showing better generalization.
Yeah, it fundamentally challenges the assumption that advanced reasoning in AI has to be language-based. For certain domains, thinking visually might just be better.
It really makes you reconsider the pathways to intelligence. So here's a thought to leave you with. If we can teach AI to reason and plan by manipulating visual concepts directly, almost like a human sketching out ideas or visualizing a solution, could this unlock entirely new kinds of problem solving? Could it lead to forms of AI intuition or creativity that are fundamentally different, maybe even complementary to the logic we see in language models today?